Hello children, this presentation is a summary of your 8th chapter, Newton's laws of motion, that you have studied in your last few classes. So in this video, we'll summarize the following. What are forces? What is the meaning of an unbalanced force? And then Newton's 3 laws of motion. His first law, which is the law of inertia. His second law, the famous F is equal to ma equation, and what are action and reaction pairs. And then we'll move on to momentum and then the conservation of momentum principle. So what exactly is a force? A force is nothing but a pull or a push. Right? So if an object is at rest, the force makes it to start to move, or if it is moving already, it makes it move faster or it slows it down. Basically, a force is something that causes a body to accelerate. That is, it changes its velocity. There could be many forces acting on a body. So we need to take the sum of all the forces, and we should take both the magnitude and the direction of the forces into consideration and determine the next net force. If the net force is 0, it means that the forces all balance out each other and there is no acceleration and the body remains in its original state. Like here, there are two girls pushing the box with the same magnitude of the force, but then in opposite directions. So the net force in the box is 0 and hence the box remains in its original state of rest. But if the forces are unbalanced, there is a net force in a particular direction and this causes an acceleration in that particular direction. Here in these pictures, the net force is towards the right? And so the box starts moving towards the right. What is inertia? Inertia is the tendency of an object to resist changes to its velocity. Right? If an object is at rest, it will tend to remain at rest, and if it is moving, it will tend to keep on moving. Right? So what does this mean? Look at this example. So we see that this giraffe is moving in a car and the car hits a wall and stops. But the giraffe tends to continue to move and hence it falls forward. So this is the reason that we wear seat belts in cars, right? To prevent accidents like these. Right? And it's also the reason why when a bus stops suddenly, we fall forward. So what's the relationship between mass and inertia? More the mass, more the inertia. This just means that it is more difficult to change the velocity of a heavier object than a lighter one. As you all know, it is much easier to throw a lighter ball, thus giving it more velocity than a heavier one. So now let's look at Newton's laws of motion one by one. Newton's first law is the law of inertia. It states that an object at rest will remain at rest, okay? And an object in motion will continue to be in motion at constant velocity unless it's acted upon by some unbalanced force, okay? So this means that a ball on the ground is going to remain there on the ground unless you kick it. By kicking, you give it an unbalanced force. And a ball in motion is going to keep on moving unless it is stopped by something like a net, right? But then in real life, right, we see that suppose a moving ball on the ground does not keep on moving. After some time, it comes to rest, right? So what is the force that makes the ball come to a rest after some time? This force is called the frictional force, and we can't really see it, but this is the force that makes the ball stop moving. So So if there is no friction, there is no air resistance, a moving ball will keep on moving for forever. That's what Newton's first law says. And this we can see in outer space. When there is no air and there is no friction, a screwdriver, say, that is thrown will keep on traveling forever with the same velocity. So now that we know that a force gives an acceleration to a body, how do we go about measuring this acceleration? Right? Newton's second law of motion helps us with this. So it says the acceleration of an object, right, is directly proportional to the force and inversely proportional to its mass. So what does this mean? It means that if we applied a force, an object gets a certain acceleration, right? And if you apply more force, the acceleration is greater. The speed increases faster. This is very obvious. And another thing is, for the same force applied, F and F, right? If the mass of the object is increased, right, the acceleration is lesser. So over here the mass is less, the acceleration is more. Over here the mass is more, the acceleration it gains is less for the same force applied. So A, the acceleration A, right, is directly proportional to the force applied and inversely proportional to its mass. Correct? And putting it together, we get A is equal to F by M, or F is equal to MA. Right? So we have a new unit called the Newton to measure force. And 1 Newton is the amount of force, right, required to give an acceleration of 1 meter per second squared to an object of mass 1 kg. So this is a very important formula that all of you have to remember. F is equal to ma. Here mass is measured in kg, A is measured in meters per second squared, and F, then the force required, is measured in newtons. So let's take an example. Right? If we apply a force of 100 newtons to an object of mass 500 kg, what will be its acceleration? So we just use this formula, F is equal to ma, right? F is given as 100 newtons and mass is 500 kg. So what is E? A is equal to F divided by m. So that is equal to 100 newtons, right, divided by mass, that is 500 kg, right? And what do we get? We get 1 by 5 or 0.2 meters per second squared. So what does this mean? If we push a mass of 500 kg, right, with a force of 100 newtons, right, this object is going to start moving forward with an acceleration of 0.2 meters per second squared. So let's look at another example. How much more force is required to move an object of mass 400 kg and another object of mass 40 kg to give both objects an acceleration of 10 meters per second squared. So over here, let F1 be the force required to move the 400 kg object and give it an acceleration of 10 meters per second squared, and F2 be this force, right, the 40 kg object. So what is F1? F1 is equal to ma, the famous equation. So over here we have a 400 kg mass and the acceleration required is 10 meters per second squared. So we get a force of 4000 newtons is required. And what is F2? Is again the 40 kg mass, right? And we have to give it the same acceleration of 10 meters per second squared. So we need a force of 400 newtons. So the extra force is, what is the more extra force required is F1 minus F2. And that is equal to 4000 newtons minus 400 newtons. and that is equal to 3600 newtons. So this much force, extra force is required to move this 400 kg mass than the 40 kg mass. Now let's look at Newton's third law. Right? It just says that every action has an equal and opposite reaction. What does this mean? It means that we have two objects, right? 1 and 2. Right? If object 1 exerts a certain amount of force on object 2, then object 2 exerts an equal and opposite force on object 1. So over here, look at this example. This man wants to jump on the deck. So what does he do? He pushes against the boat with a certain amount of force. That's the action. And the boat gives him a push, okay, in the opposite direction, and that's the reaction and helps him to jump on the deck. Here in this air balloon, the action is the air rushing down, coming out of the balloon, right? And the reaction is the balloon going up. Here in this example, like when a bullet is fired from the gun, right, the gun exerts a certain amount of force on the bullet, and that's the action. And the bullet in turn exerts a certain amount of force on the gun, and that's the reaction. And that's why the gun recoils to some extent, goes back. Even the simple act of walking, right, on the ground is an action and reaction pair. Our foot pushes down and back on the ground, right? And the ground exerts an equal and opposite push on us, okay, which helps us to move forward. The term momentum intuitively means how difficult it is to stop something that is moving. It is very difficult to stop a very heavy object that is moving, right? It's also very difficult to stop an object that is moving with a very high velocity. So we define a new quantity called momentum, which is nothing but the product of an object's mass and its velocity. Right? So rho, which depicts momentum, is nothing but mass into velocity. So let's look at something called the rate of change of momentum. What do we mean by this? We mean it is nothing but how fast the momentum changes. That is, change in momentum over time. Right? So if we can calculate something called the final momentum, we subtract the initial momentum of an object and divide it by the time, right? We can find the rate of change of momentum. Always remember, rate is something which tells us how fast something changes with respect to time. Like rate of change of velocity is acceleration, right? So the final momentum, suppose v is the final velocity, right? So m into v will be the final momentum of an object. And initial momentum of an object is nothing but mass into the initial velocity u. Correct? So this we divide by the time t. This should denote the rate of change of momentum. So this we can rewrite it as m is common, the mass does not change, the final velocity minus initial velocity divided by the time taken. And this is nothing but, we know that v minus u by t, what is this? Is the acceleration. Final velocity minus the initial velocity divided by the time taken is the acceleration, right? So ma. So now you all know what ma stands for. What is ma? Ma is nothing but the force, right? So force, we get another meaning for force, right? It's nothing but the rate of change of momentum. That is how fast the momentum of an object changes is nothing but the force. Here we have three vehicles, a bus, a car and a train, right? All having different masses and traveling at different velocities. But if we calculate the momentum for all these three, right, look at the momentum all turns out to be the same. The mass 9000 into the velocity 16. The momentum of the bus is something like 1.44 and 10 to the power of 5 kg meters per second. And similarly, the mass of the car is 1800 kgs. multiplied by its velocity is so much, and the mass of the train is very large, but it's moving very slowly. So if we multiply these two, we get the same quantity. And the momenta are all the same for these three vehicles. What does this mean? It means that the force required to stop these three vehicles is the same. Let us now look at a principle called conservation of momentum. Say we have two objects A and B of masses ma and mb moving with velocities ua and ub. Right? These objects, they collide, and after collision their velocity changes. They start moving with velocities va and vb. Now during the collision, right, object A is going to exert a force of FAB, say, on object B, and object B exerts a force on object A which we call FBA. Right? Now according to the Newton's third law, right, FAB should be equal and opposite to FBA because they are an action and reaction pair. And what is FAB? FAB is nothing but the mass of object A into its acceleration. That is, what mass of object A into the velocity after impact, right, after the collision VA, minus the velocity before the collision UA divided by the time taken. And FBA is the mass of object B into its acceleration, that is mb into vb, its velocity after the collision minus the velocity before the collision over the time taken. So according to Newton's third law, we can equate these two with a minus sign. Correct? Yeah. So now and if we expand this, right, this t, the time interval t, time t can be cancelled out because it's the same instant, the time instant of the collision, right? The time interval has to be the same, right? So if we rearrange this is what we get. Now look at this a little bit more closely. What is MAUA? It is the momentum of object A before impact. This is the momentum of object B before impact, and this is the momentum of object A after impact, and this is the momentum of object B after impact or after the collision. Right? So the sum total of the momentum of the two objects before impact is equal to the sum total momentum after impact. Right? So this is what we mean by the conservation of momentum principle. Right? The momentum remains, the total momentum before and after collision, it remains unchanged, provided of course no other external force acts on these objects. Let us now look at an example, right, that demonstrates the conservation of momentum principle. So suppose we have a 1000 kg car moving at a certain velocity of 20 meters per second. It hits a stationary parked car of mass 800 kgs. Right? So because of the collision, because of the impact, both cars start moving together at a certain velocity, and we need to find this velocity. So we have, this is our initial mass, right? So this is MA, and MA is equal to 1000, and UA is equal to, the initial velocity of this car is 20, and MB, right, is equal to 800, and the velocity UB is equal to 0, right, because it is parked. It's a stationary object. After the collision, the masses remain the same, but then they both start moving with the velocity of with a common velocity. So VA is equal to VB, say some velocity V, which we need to find out. So suppose we use this formula, we get 1000 into UA, that is 20, is equal plus the momentum of the second parked car, right? That is 800 mass of that car into its velocity, which is 0. Initial velocity is 0 because it is stationary. That should be equal to 1000 into the final velocity of this car, that is v, right? Plus that 800 kg car also starts moving with the same velocity v, which we have to find out. So what do we get here? We get 20,000 plus 800 into 0, that is 0, should be equal to, here we can take out v common, right? V, some common velocity v, into 1000 plus 800. In other words, 20,000 should be equal to v into 1800. If we solve for v should be equal to 20,000 divided by 1800, right? And we get something like 11.11 meters per second. This means that after the impact, both the cars start moving together with a velocity of 11.11 meters per second. Thank you, children.